Hello everyone, today I want to show you how you can solve this problem up here. We have a triangle, it's an isosceles triangle, it has two equal sides. It is inscribed in the you could say in the origin of the xy plane, and we basically want to find the area of the region it encloses with the x and y axis, okay? And we're calling that region R, okay? Now, I want to use a double integral to solve this, okay? Because even though I think it is a trivial problem to find the area of this, that is just base times height divided by 2, I think it would be useful to show you how you can solve this problem using a double integral, okay? A definite double integral. So we're going to begin with a very simple idea, and we're going to say that, well, we have this region here, and we can split this region into very thin strips along the y-axis and along the x-axis, okay? So you could say, well, we can have a very thin rectangle that has a width of dx, and you could say we have another super thin rectangle, these are really hard to draw, of a height dy, okay? Notice that these two guys will create a square or a region. I guess you could argue maybe it's a square, I don't know, it depends on the size of dx and dy, that's irrelevant. You're gonna get a square or a rectangle in here. And if we add up all those small rectangles, we're gonna get the total area of R, okay? And that is what we're gonna do. So we're gonna say that the total area of R should be, and I'm gonna use the double integral now, it should be the sum of all the small areas dA, okay? And I am using a double integral because notice that dA is gonna be, of course, dx dy, okay? So think about this, dA equals dx dy because a really tiny chunk of area will be equal to the length times the width, or the height times the width of this small rectangle here, okay? I think you have to try to visualize that, and if you understand that and you feel okay with it, we can move on. So we have this integral here. Now, we just need to figure out what are our bounds of integration, and that's where it becomes a little more difficult. So anytime you have a region that is not rectangular, in this case, this is not a rectangle, you're gonna have to do a trick, and this trick is you're gonna have to express the variable you're integrating with respect to in terms of the other variable, and you're gonna have to do that using a function. You're gonna have to come up with an expression that allows you to write the variable you're integrating with respect to in terms of the other variable, okay? Now that may be a little weird, but let me show you what I mean. And to do that, I first want to switch the order of integration, and that means what I'm gonna do is, instead of writing dx dy, I'm just going to write the integral of dy dx, and this is totally legal. This is just an arbitrary choice, and you can do this without any consequences, as long as you haven't, put in the bounds. In this case, you can do it, and everything's fine. Now, what I want to show you is this. If we integrate with respect to y, what would you say are the lower and upper bounds? Now, you could say it is 0 and 1, but you would be incorrect, because y is varying with respect to x in a way that is not, you could say, rectangular. In this case, y will change depending on the location of x you're at. So that means that to integrate with respect to y, you have to write a function of x, and you have to consider x in some way, okay? Now, notice that this is a line, this is a linear function, and we can write y in terms of x by, finding an expression for this line. So let's do that now. We know that line could be written as mx plus b, and this is the slope and this is the y-intercept. And now this is a very simple function. The slope of this thing should just be equal to -1. Okay, because we're dropping, so it is rise over run. Our rise is going to be -1, and our run is going to be +1. So that should be minus x plus 1, okay? So notice that when we are at x equals 0, we should get 1. So this is our function. Now, we want to put this function that describes the upper bound. So here you have to visualize, when you're finding the bounds of y, you have to find the lower bound and the upper bound. The lower bound in this case is very obvious. It's going to be y equals 0. But the upper bound will change the upper bound of this rectangle, and the upper bound of these strips will change depending on the location of y, of x that you're at, okay? If you're at a small value of x, you're gonna have a greater y. And to account for that, you have to do this. You have to find an expression for y in terms of x, and then you're gonna put that expression as your upper bound, okay? Because depending on the x value you're at, this expression will give you a different number, okay? And that is how we can account for the idea that the upper bound is variable, okay? And now we do what we would typically do, although we should first, before integrating this, we should find the bounds for x. Now the bounds for x are actually much easier because anytime you have nested integrals, the outermost bound will be just a rectangular region, or you could treat it as a rectangular region. In this case, notice that x ranges from 0 to 1, and that is to some extent something we're saying. So basically we can say this goes from 0 to 1, and when we do this, we're also saying that this 0 to minus x plus 1 will have a domain, or at least this upper bound will have a domain of 0 up to 1, okay? I hope that makes sense, and that is the reason behind why we do this. So now let's see what this would give us. I'm going to continue down here. So now we just have to integrate this, and now this is just very simple. Remember that you just have to do the innermost integral first. So in this case, we're going to have the integral of 1 with respect to y, that is just going to be y, and then we want to integrate that with respect to minus x, with, well, evaluate it at these different points. And now we want to integrate with respect to x, okay? And this thing is going to give us the integral from 0 to 1 of, now this inner expression is going to be minus x plus 1. Now you integrate with respect to x, and let's see what this is going to give us. So this is something really easy. This is something you can do if you've taken a single variable calculus class before, which I assume you have if you're looking at double integrals. This should be minus x squared divided by 2 plus x, and then evaluate it at 0 and at positive 1, okay? Now, if we plug in 1, the 0 is not going to matter, so we're going to have minus a half plus 1, which is also a half, okay? And a half, 0.5, is what we expected to get if we had just done the area of a triangle equals b times height divided by 2. B equals 1, height equals 1. That's going to give you 1 times 1 divided by 2, that's a half. And that is the same number that we got using double integrals, okay? And that is pretty cool. It shows you that double integrals work. And I hope, well, this has been a useful way to show you what happens with your bounds. This is probably the trickiest part about doing multiple integrals. You have to be careful with the bounds. And let me just go over the idea again real quickly. When you're integrating with respect to y, you need to know what is the maximum value of y and what is the minimum value of y, okay? The minimum value is going to be y equals 0, okay? That is hopefully trivial to notice. But then the upper value of y, depending on what x value you're at in your region R, you're going to have a different upper value of y, okay? Because notice y is a function, and the height of y, or the height of your rectangle, will change as you go along x, okay? And that means that the height of your rectangle is a function of x. And that is why we write the upper bound as a function of x, okay? The upper bound is variable, and it varies with respect to x. And that is why we write the upper bound as a function of x, okay? I am saying it multiple times, but it's very important, and I hope you can get that understanding. A lot of people just learn that you have to put in an expression here, but really the intuition behind it, I think, is very important. And I think if you've gotten this far into the video, hopefully you understand it by now, or at least you can have a better sense of intuition. So yes, this is the final answer. I hope you enjoyed this video, I hope you learned something, and see you in the following one. Bye.